All right, so today I'm going to talk to you a little bit about flexible network analytics in the cloud. And to kind of set it up, network analytics is one of those things that seems like it ought to be awfully simple, but it really just kind of isn't. And it seems like any half-decent accountant could do this. It doesn't really take a network engineer, but unfortunately, it's actually quite a bit harder than that. And some days it just becomes this very repetitive process, and you feel a little bit like Sisyphus. You remember this guy Sisyphus from Greek mythology? He was condemned to roll a rock up the hill every day, and every night it would roll back down, and he got to do it all over again and again and again. Well, obviously no one wants to live their life that way. So I'm going to talk a little bit about how to get out of that mode of things. Now, we're not talking about how to get to be this crazy, perfect world or something like that. It's going to be a little more of a journey. It's going to be a little bit of a climb to get to where we're going. But I think the climb is worth it, and at the end we'll get to a place where we can see something that's pretty interesting. So here's the kind of outline of what I'm going to talk about. I'm first going to talk about some hard realities, and I'm going to talk a little bit about how we cope with those realities. And then I'm going to talk about a programming model that we found that really helps to bring some of these ideas together about how to approach this problem. And then I'll get into a little bit more detail with some very simple code examples, and then finally just talk about where we've gotten to. Okay, so the hard reality is that network measurement is much harder than it would seem. And the first reality here is that everything's a mess. We want it to be neat and tidy, but the thing is, despite the best efforts of our vendors, telemetry seems to be one of the last things that's focused on. So things are messy, they're irregular, maybe you have to go to some proprietary MIB, maybe you scrape the screen to get the data you want, or even if you don't have to do that, you run into bugs, all kinds of other things like that. So at the beginning of the day, or the fundamental thing to start with is you just have to accept the fact that things are a mess, right? What we want it to be is to look something like this, to look like this beautiful, well-built building, but that's not really what it looks like. In fact, it's really a lot more like this, right? I mean, sure, this thing meets the minimum requirements to be a building. It'll keep the rain out, maybe, at least through the next storm, hopefully. But at the end of the day, it's not really what you want, right? So the first hard reality then is the world is not neat and tidy, right? We kind of accept this. We know this as adults, that the world's not neat and tidy. But we sometimes forget that the data we're getting is also not going to be neat and tidy. Even though it's produced by these devices, which are running programs written by intelligent people, things are still not neat and tidy. So you really need to accept this fact that your data is also not neat and tidy. So you need to accept it, you need to design for it, and you need to live with it. I mean, you could even invite it over for dinner just so that you can really get comfortable with it. But the idea is things are not neat and tidy. So that's the first struggle when it comes to doing this sort of network analytics. So the second one is that things change. No matter what you do, the world moves on, things change, things get harder, they change, you get new requirements, you get told, oh, I need to know this now, but before you told me you needed this. So, things are always in motion, And so, first request was to build something kind of like this, but then it turns out, by the time you were done, your company needed something that looked more like this, right? Two very different buildings, but they're both buildings, but they're very different. So what you needed yesterday probably won't be what you need tomorrow. And these things take time. It's a lot of work to build these sorts of systems. So what are you going to do about that? So you have to build something that will not only work for today, but will also work for tomorrow. So my key insight here is don't make decisions today that you can't unmake tomorrow. And what I really am talking about here is saving raw data. Basically, you want to keep your data in as raw format as possible, because any decisions you make today are decisions you can't unmake tomorrow, because if you've thrown away any part of your data, then you don't have it anymore. All right, the next hard reality is that there's always more. People always want to collect new statistics. They always want to collect, or there's new devices coming online, or there's new analyses you want to do. So there's always more to do. And this is kind of like population growth. And there's this picture is kind of fun to me because it's an interesting approach. In the Soviet Union, they had a problem with population growth, and what their solution was to build these apartment buildings all look the same. And although I'm not sure that I love the idea of making cookie-cutter apartment buildings for people, I do think your infrastructure, the things that you're using to run your analytics, should be pretty cookie-cutter. You want to be able to spin up new versions with no problems. You don't want them to be all unique. You want them all to be the same. So, since there are always more devices coming online and more telemetry that you want to be gathering, if you build this yourself, your storage and your compute will be the same size, right? As they are. So your compute and storage will be the same size tomorrow as they are today, which means that they're trying to do more with more data, but have the same size. So this is, I think the value proposition here, and this is the pretty clear value proposition for the cloud in general, is use the cloud to scale, right? The cloud is elastic, it scales both up and down, and at the scales we're talking about, it's effectively infinite. So you don't have to worry so much about this infrastructure. Okay, and so the fourth reality is that nothing is ever really done, right? No matter what we do, we have our aspirations, we have our goals, we have these grand plans of these things we're going to build, but at the end of the day, things don't get done because priorities change, because the resources we have outstrip the amount of, aren't big enough to actually be able to implement some of these things. So we end up in a situation like this. I don't know if you're familiar with this building. It's called the Tower of David, and it's in Caracas in Venezuela, and it was started in 2000, and today it still looks like this. It was never finished. It's unfortunately due to a banking crisis, but I think it's an interesting reminder that we have these grand visions for these big buildings that we're going to build with our projects, but sometimes they don't get finished. And so what we're going to do about that. So since nothing is ever really finished, even if you do sort of complete what you originally planned to do, you end up in a situation where things have changed and you have to add new features and stuff like that. So, our resources are limited. So I think what's really important here is to focus on being able to talk about what you want to get out of your data, right? So when it comes to data analytics, what you want to know, you don't want to spend a lot of time messing around with the how, you want to spend more time on the what. What insight can I gain from this data? Not so much, how do I build the infrastructure to process this data? Okay, so I kind of talked about these four things. The first thing is it's a mess, right? So design knowing that things won't be neat and tidy. Secondly, things change, so keep your options open by storing raw data. There's always more, rely on the cloud for scaling. And finally, it's never really done, so spend as much time as you can on the what and not on the how. All right, so I kind of set up the problem, and this is kind of, I've been involved in this area for many years, and so I've definitely seen these issues. And a few years ago, I was having a conversation with one of my coworkers about, well, how could we leverage other infrastructure or things like the cloud to help us without giving up too much control? Like, where can we find value here and make lives easier for ourselves? And we had started by going into looking at various different options. And we had looked at this thing called the Lambda architecture, and there's a link to it later. And that was really interesting, but it required writing a lot of stuff. And so then a little bit later, we discovered this thing called Apache Beam. And Apache Beam is really three things. It's a programming model, and I'm going to discuss what that programming model is in the next couple of slides. But there's also two other important components to it. The second is that it's an SDK for writing things that appear to this programming model. So it's not just a theoretical thing. There is a concrete version of it. And the third thing is there are runners for various distributed processing backends, right? So things like Apache Spark and Flink, or there's the hosted version on Google Cloud called Dataflow, and there's even a local version that you can sort of do testing with. So there's these kind of three things that I think make it very appealing. It has a very high-level conceptual model, it has an actual implementation, and it kind of runs on a variety of vendors. So I'm just going to quickly go through where did this Beam thing come from. So you may remember many years ago, MapReduce was a big deal, right? This is sort of how Google dealt with generating their index. They had this huge data set, and how do they process it every night? And it was this paper that came out. It was pretty interesting, but it was just a paper. And then Google went on to have more and more challenges about how to process data, and they kept writing papers about it, but they didn't ever share any code about how to deal with this. So because these were interesting ideas and good ideas, a whole ecosystem open source project kind of sprung up around this, right? Hadoop being the first of these, but many other ones like Spark and Flink, some of the other ones I mentioned. And this is fantastic because these ideas are getting their concrete implementations in the world, and they're open source, people can use them. And then, so that's really pretty fantastic. But they're all a little bit different. They don't all really work together. And so recently, Google released something called Cloud Dataflow, which was sort of the precursor to Beam. And it was the first time that Google actually let the public buy, or at least be able to use some of the things they've written about in these papers, right? This is the descendant of all of these papers. And they decided that this was a general enough model that they wanted to share it with the community. And so that's what Apache Beam is. And it's this general purpose model for processing these large data sets. Okay, so just real quickly, then why do I like this so much? I think one of the biggest wins is it's a unified model. It handles both batch processing and stream processing with the same code base. So you don't have to write one set of code to handle streaming use cases and another one to do your batch jobs. You can write them both using the same SDK. It's portable. As I mentioned earlier in an earlier slide, that you could execute it on a number of different runners. You're not locked into one vendor. And it's extensible. It's software. You can actually get in there and change things about it. And it's a very active open source community. In fact, just yesterday, they announced Beam 2.0, which was the first declared stable version. So that's a big milestone for an Apache project if you're familiar with the Apache way of doing open source projects. Okay, so just to give you a little bit more idea, I've talked at high level what this Beam thing's about, so let's get a little more specific. What's the deal here? So there's kind of 4 questions that Beam gives you ways to answer. And the first one is the really obvious one. What do you want to do with your data, right? What are the results that you want to calculate? So that's kind of, any system can do this, right? That's the fundamental question. But then it takes and adds 3 more questions that it gives you ways to answer. The second one is, where in event time do you calculate your results? So if you think about a traditional batch system, they would generally just process things in the order that they were read out of the database or off the disk, and without any regard to the timestamp on the event. And this works well if all you're trying to do is an aggregate overnight or something like that, but it's not so great if you're trying to get finer grained things. So this is the first sort of question that we have to answer. Now, Beam's certainly not the first thing to think about this, but it's a fundamental thing, and you get to control how your system processes things by looking at the timestamps. So that's great, but the next thing is, and this is the next 2 are kind of where Beam really shines, is so you have these event timestamps, but as you're processing your data, you may actually want to produce a result. This might be like a streaming job where you're trying to give up to the minute results. And so you need some sort of heuristic about, okay, I've seen this, I'm this far into my processing, but I think I've seen all the events up to this timestamp so I can emit something. And that's great, and that usually works, but when it doesn't, the 4th question is about how you take care of refining things later. If later in your processing you find something that has an earlier timestamp, how do you update that? So here's a kind of a quick graphical view representation of that. So on the left, we have classic batch, right? Basically, you take your entire data set, you really don't have any regard for the timestamps or for the processing time. You just want to add up all these integers. And in this case, they add up to 51. In the second one, you actually start paying attention to the timestamps. And I should point out that the event time, the time that's like that associated with the event, is on the x-axis, and the processing time is on the y-axis. So here, we break things up into windowed segments, and then add up the numbers inside each of those and get sort of for that window how much we saw. And if you wanted the total, you can just add up all the windows. Now, to give a little bit clearer idea with the streaming case and the when question, right? You can see that for the first window, in event time, we have 2 events, but in processing time, one of them comes very late. And so that's the one that's in red there. And when we produce a result for the first window, we actually don't include that number. We just go along. And so in the first case, if we don't have any sort of correction built in, then we kind of miss that in our streaming approximation. But that's the last thing. In the 4th one, you can see that we emit 2 events for the first window. And that's because later in processing time, we discover another event that is relevant to the first window. We said, oh, I made a mistake there. Here's the actual value for the first window. So this is kind of the conceptual model that really helps to understand what sorts of things we can do with all these events. Okay, that's great. I kind of talked about sort of high-level things we can do here. Now let's get into like an actual example. So I'm going to go one layer down and talk a little bit more specifically about some of the things about Beam, and then I'm actually going to do a quick code example that will explain some of the things we're able to do here. So, and actually this first one, the first 2 actually aren't so much about Beam, but kind of how we're using Beam. So I've mentioned a lot about raw data, right? I've said, and I'm probably going to say raw data a few more times, and you're probably going to get tired of me saying it. But one of the key tenets here is to make this immutable data store a read-only repository of all your raw data. So avoid the temptation to massage it into some format that you think is probably what you want. But if you lose information, it's gone forever. And also sort of avoid the temptation to go in and change things later. The more you muck with this, the bigger chance you have of screwing it up, right? The more you go in there and touch it, the more chance you have to make mistakes. So the benefits of having this is you get to change your mind later, right? If you decide you need a different analysis, you can then in the future go back and do a different analysis because you still have the raw data. And if you make a mistake, you can go back and reprocess your raw data again with updated code and produce new results, which actually give you the correct answer. So, I don't know about you, but every once in a while I make a mistake. And so this to me is a super comforting thing about this. I can be a lot more bold about my analysis and try new ideas because I know, well, if I made a mistake, it's not the end of the world because I can go back and redo it. Okay, so that's great. Raw data is important to this, but raw data isn't particularly useful to human beings, right? It's very difficult for us to look at raw data. I mean, for example, you don't want to be thinking about IF indexes when you look at your interface statistics, right? No one remembers that IF index 37 is actually XE000, right? Like that's just something we don't want to do. So if you have raw data, you need a way to make it more presentable, more palatable to human beings. And that's what these views are about. So a view takes the data the raw data you have and produces an intermediate representation that has more value, that joins things together. So for example, you might correlate the IF name to the IF index and use that as part of it. Or, router counter data is just that. It comes as absolute counter since the last router reset, right? So you get this ever-increasing number of bytes that is passed through the interface, but that's not really what we want to know. We really want to know how many bits per second are passing through the interface right now, right? So this is another use for a view. And the interesting thing about these views is they can stack on top of each other. So you can make one view that maybe converts your 30-second measurements into rates, and then maybe you can have another view that takes that and turns it into 5 minutes where you have averages and maybe 95th percentile or something like that. And you can continue to stack those. Or you could say, oh, well, I have a bunch of interfaces that have similar semantics. Maybe they face the same customer, they face the same peer, and I want to add them up. So you can create an aggregate view that sort of adds those things up. Now, I've talked a lot about SNMP, and that's because where we are in our process right now is we're focused on SNMP, but I'm actually really excited about this for NetFlow as well. And I think, a lot of the top talker type stuff, traffic matrix type stuff will fall out of this kind of approach very easily as well. Okay, so I promise there's some code coming. So before I get there, though, I need to talk a little about some core abstractions in Beam. So there's kind of 3 things here that kind of go into the idea of the pipeline. So the first one is this idea of a P collection. So a P collection stands for parallel collection. And this is a distributed multi-element data set. It's really kind of a wrapper for whatever type you want to define around your data. And then it provides a mechanism for distributing it to all the workers. The second important concept is a transform. And a transform takes a P collection in and produces a P collection. And it is what actually does the work of your analysis. So you get your data in, you perform some transformation, and you output your data for the next step of the pipeline. And then the next idea that is important is these pipeline I/O setup. So basically, this is what reads data from your data warehouse to produce a P collection to feed into the pipeline. And then when you're done, it can take the P collection and write it out to disk or to wherever you need to send it. So these 3 things kind of work together to build a pipeline. And a pipeline looks something like this. There's input, there's a P collection, there's transforms, which each use P collections between them, and then finally, the last P collection, and then you generate some output. So why are these things important, right? I talked earlier about thinking about the what, and so not so much about the how. So using these allows you to define the what. You refer to some sort of I/O to tell your system where to get its data from, what data to use, where it lives. But you don't have to worry about the low-level details. Beam will handle that part for you, the low-level how, right? Same thing with P collections. You group the data together in useful ways for the analysis, but you don't have to spend the time of figuring out how to get it on all these parallel workers. Beam will take care of that for you. And finally, transforms, again, sort of the wrapper for your actual code. And you write the code, and this is maybe the hardest part, right? Because you actually have to write some code, but the process of distributing it to a whole bunch of workers, that's taken care of for you. Okay, so here's a very simple example. And there's a fair bit of code on this page, and if you note, there's a URL at the bottom where you can look at this in more detail. So I encourage you not to get too caught in the details here, but instead look at the high-level picture of what we're doing here. So say we've got a list of interfaces, and we want to sum up the total traffic for each timestamp across all of them, right? Maybe this is, like, again, what I mentioned before. This is all the interfaces facing a customer, and they want an aggregate view of how much traffic's going into and out of that part of the network. So should explain a little bit about the syntax here. On the left, you see this thing like a string that says like read, and then there's these greater than, greater than. So the thing on the left is used by Beam to sort of as an annotation that tells you what this pipeline step's doing, and the thing on the right is actually the code that implements that step. Okay, so in the first line, what we're going to do here is we're going to read some text in. And what all this will do is actually basically read one line at a time. Well, it'll read in a bunch of lines and put them in a P collection. So now we've got all these things in a P collection, but they're just lines. In this case, I made them CSV. So on the next line, what we do is take and split on the commas to break out our fields. So we get things like IF name and IFHC and octets, things like that. And that produces an object, though, which we then pass to the next step. So the next step takes that object and turns it into a key value pair. So it extracts the device name and the interface name, uses that as a key, and then puts that whole object as the value. And then we're able to run this group by thing using the Beam group by key, which will basically cluster all of the things with the same key to the same set of workers, or to the same, and then we get to the point where we can actually compute our rates. So there's a function here, and this function is not shown on this slide, which will take the difference between each of the counter measurements and divide by the sort of your measurement interval and multiply by 8 to get your rate, right? And then once we've done that, what we can do is go to the next step. Now we do another group by operation, right? Instead of grouping by the interface, we want to group by the timestamp because we want all the things timestamp to line up. So we'll go ahead and do that in the next two steps. And then finally, this line that says sum by timestamp will take all of those data points for that timestamp, add them up, and then it produces simply a timestamp and a total value. And then the last two lines are just kind of about formatting it. I formatted it basically back to CSV and write it back out. So, this isn't rocket science, obviously. And the algorithm that I've implemented here is relatively simple. It's done by countless other programs. But what I want to show you is it's not that hard to implement it in this way. And the advantage you get is that Beam now can scale this for you, right? You can run this on hundreds of workers. So this could scale easily to millions of interfaces. It doesn't need to simply just do 10, right? So I did say it would scale to lots and lots of interfaces. So I did sort of neglect one thing, which is I simplified this example a little bit to make it easy to understand on the slide. There's not major differences, and I'm getting into that a little bit in the blog post. But there are some details about making sure that things will work well in a distributed system, which I'm not going to go into that now because it's a little bit complicated. But the blog post covers that in some detail, and there'll be a subsequent blog post that gives a lot more detail about that. Okay, so that's great. We've got some code that does this. There are some trade-offs here, though, right? The way I like to think about this is good, fast, cheap. Pick two. You can talk about having complete data. You can talk about having data quickly, or you can talk about having it cheaply, right? And you can kind of usually get two of those, but sometimes getting all three can be difficult. So completeness is sort of the idea that I've been able to look at all my data and do a complete analysis of it. And this is an important thing for, say, billing, where you want to be sure that you're giving, an accurate number. But the problem is you have to wait for all your data to show up, and sometimes that's not what you want. And so the other dimension to think about here is latency. Sometimes you want low latency because you want to be able to be reactive to what's going on in your network. You want to be able to see things in real time. And so you may be able to accept a slightly less complete solution in favor of getting the answer more quickly. And as I showed up before, Beam actually gives you the ability also to refine those things going on later. And then finally, cost is sort of something you can use to massage these dimensions a little bit, and it's kind of up to your specific project whether or not spending more money makes sense, or if you can sort of live with the limitations of the other things. So I've talked about stream and batch. Let me just give a few examples of when you might use stream versus batch. So streaming is for real-time insights, things that you need to know pretty quickly. Current network load, operational awareness, threat detection, anomaly detection. This tends to be a little more expensive. It seems to me that the main cost driver in the cloud is how much CPU time you use, not so much how much storage you use. So with streaming, you've got VMs running all of the time, which means you're spending money all of the time. Data at rest, you're not spending any money for that. Beam tends to think of these unbounded data sets. There's a little bit of subtlety in that. I'm not going to go into that, but it tends to think of streaming as unbounded data sets. Now, batch is kind of the other end of the spectrum. It's more about precision, right? It's about billing, or it's for results that can wait a little longer, maybe traffic planning, capacity planning, things that you don't do every day, or certainly not every 5 minutes. But you might, but you do want to do them once a month, once a quarter, something like that. And they tend to be a little cheaper, again, because you're only using the VMs in bursts. You're not, sort of locking down CPUs all the time. And this sort of approach, or this kind of data set, is what Beam refers to as a bounded data set. Okay, so getting close to the end here. I said it's not going to necessarily be totally simple to get here, but I think there's quite a bit of leverage we have by looking at this kind of an approach. And so I just want to talk a little bit about what we can see here, right? I talked about those four struggles that we have, and I want to talk a little bit about how this approach sort of helps with those struggles. So the first one is, it's always a mess, right? Things are messy, and the really big advantage of having the ability of having raw data and then the ability to recompute things means that if you find a new kind of mess in your data, you just you update your code to handle that mess, and then you're able to recompute things. Also, there's always more things coming online, new things you want to find out. Again, having the raw data allows you to go back and extract new insights out of old data. And then, as new types of telemetry become available, you can add a new immutable data set, right? I talked about SNP a little bit, but you can imagine flow or syslog or things from your IDS system, any number of different inputs to the system as a whole. So you can add more dimensions of data. And then, in terms of things never being done, you always want to try out new ideas, but if you're kind of locked into your own infrastructure, you have a concern about actually stepping on top of the production, analysis. And so here you can just spin up separate resources, try some experiments. You don't have to worry about about sort of contention with the things that already do work. And as I mentioned, running batch jobs is relatively cheap. The other nice thing about this is this gives a playground so you can teach people new things. You're not locked into this sort of rigid system. You've got some nice abstractions that you can show people, and then you can say, hey, give it a try. It's just a few dollars here and there to run some of these jobs, and then you can sort of scale by giving people the ability to do it for themselves. You don't have to do it all yourself. Okay, so the last slide here. This is kind of just our experiences with this approach so far at ESNet. There is certainly a learning curve. It does take time to learn some of these ideas. I would say that the Beam is in a position where the docs aren't amazing, but they're pretty good. They're getting there. And I would say the community is very enthusiastic and very generous, so that counts for a lot. We've asked questions on mailing lists and gotten good feedback, and there's lots of good conference talks that give a lot more detail about this. You do have to adjust your thinking a little bit. So I mentioned that problem about that example, how it wouldn't scale. Well, there's a little bit of a conceptual thing you need to understand, that because this is a distributed system, you may not actually end up with all the data on one worker node, especially if it's particularly big. So then there's an extra step you have to do to sort of combine things together to get them in the same worker node when you need to do that sort of analysis. It's not a big deal, and it's actually very well supported, but you can test these things on the local runner and hey, that works, and then you put it in the cloud and you're like, hey, that doesn't work. So it does take a little bit of time to adjust your thinking. The fourth thing I'll say is we've spent a lot of time looking at the various offerings from various cloud providers, and as you probably well know, there's a lot of options out there, and you can spend a lot of time wondering what the right choice is. So, I'm one that likes to learn new things, but at some point you have to dig in and just make a decision. And we did that, and we did that with a fair bit of confidence for two reasons. One is I'm pretty confident of the choices we've made based on our study and the technical merits of what we want to do. But at the same time, the cloud gives us a little bit of freedom there as well, right? Because if we decide we actually need to move to a different database system, we can write a migration job, spin it up in the cloud, and these things are all nice and parallel. So transitioning from one database solution to another in the cloud isn't actually such a big deal. I mean, it's not something you want to do every day, but there's a path forward should we need to take it. Cost is manageable. I'm not going to say too much about what we're spending right now, but if you want to talk to me, I can give you some more details about that. But it's considerably less than what we're paying for support for, say, some of our other similar systems that we get from commercial providers. So we're pretty comfortable with that. And in the interest of vendor neutrality, I didn't put any real specific details about our vendor, or especially the specific technologies within our vendor that we've chosen. It's not that I'm shy about talking about that, but I think this talk is more about a way of thinking about things than it is about any one specific product. So if you want to talk about the specifics, I'd be very happy to talk to you about that. Okay, so that's it. As I mentioned, there's the blog post if you want to look at more detail. If you want to learn more about Beam, there's the main website. And there's these two fantastic articles written by one of the early authors of Beam. And they're great articles, just even if you're not going to use this stuff, just understanding how it works a little bit, they're really good for that. And then I'll just mention a little bit about ESNet. We do, while this software is not yet open source, it may be someday, I couldn't say for sure. We do have a lot of other open source software. I talked about some of it last year. And it's all available at that website. And if you want to see some of it in action, our visualization portal is basically open to the public. There's very few parts of it that need any sort of credentials. So if you want to see the things we're doing with network analytics, feel free to check out that site. And that's everything I've got to say right now. So if anyone has any questions, I'd be happy to answer them.
Hi, Avi Friedman with Kentic. Great presentation. So for the streaming component of what you guys are doing, are most of those aggregations generally, are they on all the raw data for recent time periods, or is it a lot of the modern streaming databases use probabilistic data structures like hyperloglog, so you get sort of 99% accurate in much lower CPU and RAM? And for some things like threat detection, that might not be appropriate because you might miss something. And for other things like top talkers on a whole network, it's completely appropriate because it's all sampled flow anyway, and there's a little bit of imprecision. So do you know whether there's that kind of probabilistic work going on underneath, and do you think about that? And does Beam give you the ability to sort of say, this streaming approach might be better for this kind of query, but not for that?
Yeah, so I would say that Beam does not dictate any of that at all. It's kind of up to your implementation of the streaming pipeline, what you want to do. So for the SNMP stuff, right now our volumes are small enough, and the things we're doing, we've been able to express that we're basically able to do complete solutions. But there's a number of, in the particular library we're using on top of Beam, there is things like hyperloglog and stuff like that, and we are going to investigate that for certain things. But since it's just code, to a certain degree, that choice is up to you. You can implement what you want, and there's a lot of people also that have implemented things already that you could reuse.
Okay, cool, thanks.
Yep. All right, any other questions? All right, well, thank you very much.